Alright, so in this video we'll discuss section 16.6 integrals for mass calculation. So we will find the mass of a planar lamina using a double integral, find the center of mass of a planar lamina using a double integral, and find the center of mass of a three-dimensional solid. So let's get started to define the mass of a planar lamina. So a planar lamina is just a thin flat plate made of some material. So in that material can vary. I mean, it may have a constant density, or like for our purpose in this section, it will have a variable density. Okay, again, keep in mind that there's different kinds of density. For instance, we know that density equals mass over volume. If we solve for m, the mass, that would give us the density times the volume. Well, this is the typical density in chemistry or physics or in a general science class. So, and well, typically you find the distance for a solid material. But there's one thing we need to understand here is that we may find density of a planar region and density of a length. For instance, let me get started from here. Mass equals density times the volume. That's 3D version. If we send this to the second to two-dimensional situation, that is the mass equals to the density times the area. And if we make this unidimensional or one-dimensional, that is the mass times equals density times the length. And well, actually, this is the one you are familiar with from calculus 2. So the mass, which is the density times the area, or the density times the times the length. Well, in Calc 2, you learn how to find the mass of a thin wire from A of length given by A and B, where the function you integrated, it was the density function. So in this class we're going to look at this into dimensions. Well, so this is this function rho of xy will be the density function, and this dA will be the differential for area dy dx or dx dy, depending on how do we prefer to iterate the double integral, whether this is vertically simple or horizontally simple. All right. So in this case, well, so typically here's the thing about units. When we talk about density for volume, we usually express it with units of mass per volume, like kilograms per liter or grams per milliliter, which is one of the most common units in your chemistry class. However, since in this case we're going to look at this mass and density in two dimensions, so we will express this as a mass unit per unit of surface area, not a volume. All right, let's have a look at one example out a few examples actually, so we can see this in action. By the way, in this video, to make it short, I will show you the exercises already completed to do this in a way of a presentation, so in a way to keep this video as short as possible. Okay, so what do we have for example number 1? They're asking us to find the mass of a planar lamina occupying the region R under the curve y equals to x squared, that is a parabola, in the interval 0 to 2, x equals 0 to 2. All right, given that the density function is given by rho of xy equals to 2xy, where x and y are measured in inches and rho is measured in pounds per square inch. So number 1, let's graph the region of integration. Well, actually we have it to the left right here. This is going to be only half of the parabola, not the entire parabola. Why is it only half of it? Because look at the limits of integration. This is going from 0 to 2. All right. So, and it's bounded above by whatever horizontal line, which in this case is, let me write it down, that is y equals to 4. And it's bounded below by y equals to x squared. Where did I get this y equals to 4, even though it was not given? So in the region description, it only says y equals x squared and the interval 0 to 2 for x. Well, 0, 0. If you substitute 0 on this parabola, you get the origin. Well, that's 0. But if you evaluate it at 2, what do you get? 2 squared, which equals to 4. So that's what gives rise to this horizontal line, y equals to 4. All right, so let's set up the double integral that will calculate the mass using this double integral right here. Let's start with that. So in this case, I highlighted the density function, which will be replaced over here, and I'm going to iterate the double integral as dy dx. That's because since we're given functions of x, and also if we look at the at the region, clearly it's vertically simple, so it would be easier if we set up the integral like this. So in the direction of y, the upper limit is 4 and the lower limit is y equals to x squared, while the limits of integration in the x direction, the lower limit is 0, the upper limit is 2, all right, from 0 to 2. So let's integrate 2xy with respect to y. That's going to give us xy squared and evaluate between x squared and 4. And notice how I highlighted those limits of integration, because these limits are going to be applied only on the y variable. As usual, upper limit minus lower limit. Okay, let me keep highlighting those limits. That'll be 4 squared minus x squared squared. Careful, because we're going to square the already x squared. So 4 squared, that's a 16 here, and x squared squared, that's x to the 4. And well, this x that we had from before, let's distribute it for the two terms right here. That's going to give us as the result 16x minus x to the 5th. And this is a very easy integral to compute. That's a calculus 1 type of integral that's integrating using the general power rule, 16x minus x to the 5th. That gives us 8x squared minus x to the 6 over 6, evaluated between 0 and 2. All right, well, so upper limit minus lower limit. So evaluating our antiderivative of the upper limit of 2, that's going to give us 2 squared, which is 4 times 8, that equals is 32 right here, and 2 to the 6th power, this big number over 6, that's going to give us 32 over 3. And simplifying these two numbers, that's going to give us 64 over 3. Notice I wrote this big 0 right here because hopefully you guys agree that if we substitute the lower limit of 0 to the two terms on the antiderivative, that's simply going to take us to 0. So that's one example. Let's have a look at the next one on the next page. Well, so this idea about can be used in physics to compute like the total charge over a region with variable density, with variable charge density. For instance, if we have this triangular region formed by the points 0, 1, which is this point 0, 1, 1, 1, which is this point 1, 1, and 1, 0, which is this point right here. So we have a charge density given by rho of x. Let me highlight, we're using a different color. So that is rho of x, y, rather, not just rho of x, that's rho of x, y, measured in coulombs per square meter. This is, because again, this is a density function. Well, so in this case, set up the double integral that finds the total charge right here, given this density right here, this density function, which is in this case the charge density. Let's iterate the double integral. Well, so given that again this region, this triangular region, it happens to be both vertically simple and horizontally simple, I'm going to go with vertically simple because it's easier to work with functions of x rather than creating functions of y. Well, so let's define the functions. The top function, that is y2, the top function, minus the bottom function y1. And in this case, well, this diagonal line containing the points 0, 1 and 1, 0 will have an equation y equals to negative x plus 1. So that's going to be our lower limit right here, and our upper limit will be simply this horizontal line y equals to 1. For the limits of integration in the x direction, those are going to be simply between 0 and 1. I think it's easy to see those limits. I mean, because we have created this triangular region with this using these 3 points. All right, again. So this density function will be replaced with this x because that's a density function. So let's integrate x with respect to y. Well, that's simply going to give us y because x is constant with respect to y, right? So integrating this y between 1 minus x and 1, I wrote instead of negative x plus 1, I wrote it as 1 minus x. It's the same thing, okay? And again, I'm highlighting this limit right here because we integrated with respect to y, x is constant, just to make sure that we substitute the correct limits in the correct what's it called, the correct variable. Okay, so what's next? Well, upper limit minus lower limit, that's upper limit of 1 minus lower limit of 1 minus x. But you want to be very careful here because this negative right here will affect the sign of the two terms inside of the parentheses. So that'll be then 1 minus 1 right here and 1 minus negative x, which becomes a plus x. As we can see, 1 minus 1, we can cancel them out. That's going to be 0. 0 plus x, that's x. And x times x right here, that's going to give us an x squared. So here all we need is integrate this x squared. That's going to give us an x cubed over 3 evaluated between 0 and 1. All right, that means 1 cubed over 3 minus 0 cubed over 3. Well, that's this term is simply going to go to 0, and this is going to give us 1/3. And notice the units here, these are going to be columns. That's because that's the unit for those are the units for charge. All right, let's have a look at the next topic here. So what about moments and centers of mass? Well, so the center of a mass defines a balancing point. For instance, we can think of this seesaw right here. It's a very classical example in physics, and also for our purpose, it's gonna work very, very well. So what do we have in this seesaw? So we have two children. Well, mass 1 at a distance 1 from the center right here. And what else do we have? Well, we have another child and with mass 2 at a different distance from the center. Well, so the idea is to have the heavier mass closer to the center and the lighter body farther from the center, in a way to keep this in balance, right? Well, so in this case, we need to use the total moment. So the total moment 1, total moment 2. So the moment is defined by the mass times the distance. So in order to keep this in balance, the moments have to be exactly the same. Well, so moment 1 will be m1 d1, that is this m1 times this d1, and the total moment 2 will be the product mass 2 times this d2. Okay, now let's work out this equation to derive essentially an equation that I'm going to highlight here. Let me highlight it. Well, actually it's at the top of at the bottom of the page anyway. Well, all right, so I just highlight it. Let me unhighlight it again. So let's define the distance distance 2. So this is mass 2, whose distance 2 is x, whatever x2, which is whatever the distance from the center of mass, and initial distance, well, that is x bar. That is where we have the average distance, if you will. For mass 1, we're going to do the same. So we're going to find this distance, which happens to be x1, minus x bar, which is this distance here in the very, well, it's not necessarily in the very middle, but it could be in the very middle. So here we will replace, let me do some highlights here. So this will be d2 equals x bar minus x2, which is x bar minus x2, and the distance 1, which is should I use green, distance 1, that is x1 minus x bar. Okay, so that's going to be this distance. So the rest of the problem is just using algebra to isolate x bar, because we want to know what is the value of x. I mean, what is x bar right here for that will keep this in balance. Well, what do we do? Well, distribute m1 x1, m1 x bar, m2 x bar, and m2 x2. So that's going to give us m1 x1 minus m1 x bar equals to m2 x bar 2 minus m2 x2. So arranging terms, because again our target variable here is x bar, right? X bar. So what am I going to do? I'm going to move this term m2 x bar 2 to the left hand side, which is this guy right here, and this m1x1 to the right hand side. So when I do that, everything becomes a negative. We can change everything to positive terms right here. Okay, and well, the idea to have all terms containing this x1, I mean x bar, is to make it the greatest common factor, and then finally find an expression for x bar, which will be given by this expression. Actually, it's the same one that we have over here. Notice I have this extra m3 x3 m4 x4 because again in a seesaw you can still add more people to play in this playground, you know, because I mean as long as the seesaw can withstand that many people, well, go for it. I mean you can add a mass 3, a mass 4, and that mass 3 will be at a distance d3 from the center, and we'll have a moment big M3. This fourth mass right there will also be at a distance d4 from the center of mass, and we'll have a total moment of big M4. And of course you can keep adding more and more and more. In the end, what do? We will add all of this. That is, in the numerator we'll have the sum of all the products of the masses and and the masses and their distances divided by the total of the masses. Where do we get this formula from? Well, that's because again, moment equals mass times distance. But well, if we solve for distance, distance equals moment over mass. But this distance right here, since in this case we are looking at the one-dimensional case, that'll be some distance x, which will be big M over little m. Now, you may have seen this formula before if you have taken a statistics course, you know, because that's used to find what we call the weighted average, and that's when you're finding, for instance, your GPA, you know, when you're taking classes that are 3 units, 4 units, 5 units. Well, those classes contribute to your GPA with a higher weight than others. You know, the more units, the more weight to your GPA. Also, this formula is used to calculate the grade in a class. For instance, because for example, our class, which goes with attendance, what else, quizzes, exams, homework, and a final exam. Well, those contribute with different percentages towards the grade. Well, so to find the average grade, you would use what we call the weighted average. But in this case, we're applying to a physics situation. All right, well, how is this useful? Well, that's because, well, what if we have a thin rod or a wire with a density that varies along the length of the road? Now, look at this bar right here. Well, look at this rod. Notice how it is on the left. It has a lighter shade of brown, and it gets darker towards the right. Well, that means that the wire here, or the rod, it's not made of a uniform material. That means it doesn't have the same material, or I mean, it has the same material, but it's not distributed evenly. That means the density at every single point will be different, right? So it's going to be a variable density. All right. So here we have this point of balance right here, and notice how we have the heavier part of the rod closer to the center of mass, and the lighter part of the rod actually a little bit farther away from the point of balance. That's again to keep the bar in balance. All right, so we want to know where should we place this bar, where in between, so where in between A and B should we place this pin right here to keep the bar in balance. And for this, of course, we're going to use a Riemann sum, believe it or not. Okay, so yeah, here is where we get a plot twist essentially, and we're going to go from basic physics and to all the way to calculus, that is using Riemann sums to describe this. Okay, so suppose we subdivide, or we partition rather, this rod in a finite number of squares, right? And I'm going to take a sample of each. This one right there that I just circled. Well, so I would like to find the mass of this, the mass of this of this partition. Well, again, the mass is given by the density times the length. In this case, we are in the one-dimensional case. But how do we get this density? Well, this density is given by a density function, because again, see the colors? It goes from light brown to a darker brown. That means the density is variable. And how does that density varies? Well, it varies in accordance with this density function rho of x. Notice the approximate symbol. That's because we're just getting a finite partition. But Riemann sums, that's going to give, if we wanted to get the actual mass, that's going to mean we need to add infinitely many of these partitions. The story, the whole story about Riemann at this point in time, right? Well, again, keep in mind that moment, I'm going to repeat this again, moment equals mass times distance, and the mass will be, not the mass, the distance x will be the moment times the mass. All right. So how do we find the moment? Well, notice how the moment right here equals the mass, right here, the sum of all the masses, times the distance, and in this case the distance is going to be some xk, this xk right here we have in our bar right there. And in the denominator, well, we divide by the mass. Well, we just divide by the sum of all the masses of all these partitions that we keep highlighting here. All right, well, so representing this in terms of of functions, well, again, this density function is what describes the density of the material. This delta x will be this delta x right there, the length of the length of the partition of the wire that we're using to come up with this formulation. And well, this xk, well, that comes from the length of the partition. All right, or the position of the partition. So, and here m, that's mass. Well, mass is defined as density times length. In a similar way, we define that here. Let me go to the very beginning. Mass equals density times volume, or density times area, or density times length. But in this case, this is for the finite case, not for the infinitesimal case. For the infinitesimal case, we use rho, our density function, as a function of x, and that distance will be our delta x. And again, if we take the limit as k approaches infinity, these sums become these integrals. And look at the definition we have at the bottom of this picture. The total moment, which is the the distance x times the density function, a function of x, times the delta x, right? Isn't that what we have here at the top? While the mass, it's simply density as a function of x times length. And again, we're looking at linear density, the one-dimensional case. Now, if we wanted to find the center of mass, that means where should we put a pin on a rod to keep it in balance? We need to find the quotient moment divided by mass. That is x bar. All right, that's our center of mass. Let's have a look at one example to see this in action. So now, suppose a thin 5-meter bar. It's made of an alloy whose density in kilograms per meter. Again, this is a linear density, not surface density or three-dimensional density or volumetric density. No, it's just linear density because it's a wire again. Or a bar. I mean, it's a bar, not a wire. All right. So the density is given by the function rho of x equals to 1 plus 2x. All right. So and we want to know the center of mass within the interval 0 to 5. All right. Let me highlight that interval right here. Okay. So in this case, x represents the distance from a particular end of the bar. So I have drawn a picture of the bar and do a pretty cool representation. Well, you'll see. I'll get to the picture in a second. So number one, they're asking us to find the mass of the bar and the location of the center of mass. All right. So let's use these formulas that we have in the definition box. Right here, this formula for mass and this formula for moment, for the total moment. All right. Okay, so let's find the mass by integrating the density function that I highlighted in green, rho of x, which is 1 plus 2x. And integrating 1 plus 2x, which is a pretty basic polynomial between 0 and 5, that's going to give us 30. And because the units are kilograms per meter, it's going to be 30 kilograms. To find the total moment, again, we're going to integrate rather, the density multiplied by x, because again, moment is mass times distance. And the mass, is the density times the length in this case, okay? So that's going to be our density function, 1 plus 2x times x. And well, here we would distribute the x right here, create another polynomial, integrate really x plus 2x squared. But integrating x plus 2x squared between 0 and 5, that would give us 575 over 6. So what do we have? We have the mass because they were asking to calculate the mass. And now we need the location of the center of mass. How do we get the center of mass? By evaluating the quotient of the total moment divided by the total mass. All right? And the moment, which we calculated in the second integral, 575 over 6, and 30 divided by 30 kilograms, and that's approximately 3.2. All right, let's make sense out of this situation. I mean, because we computed a couple of integrals, and how does that make sense? How does the physics make sense with the mathematics? Well, number one, so here we have an illustration of the rod that is 5 meters in length. All right. So notice how we got the center of mass to be 3.2. That is around here, 3.2. So that means this is where we should place pin in order to. Okay, so this is not working here. A pin to keep the bar in balance. And well, notice how it's closer to 5 rather than closer to 0. So you might wonder, why is that and why it's not exactly in the middle? Well, that's because, look at the density function. The density function, which by the way, it's it's a linear function, well, with a positive slope. So that means that the density of the rod will increase at a ratio of 2 units per meter plus 1 unit. So, that means it increases as we increase the distance away from 0. So that That's what makes that's what explains why the center of mass is at this point. All right. Okay, so let's see. How about we extend this idea of centers of mass to dimensions? All right, so to find the center of mass in a two-dimensional case, well, again, keep in mind that the moment of mass for a particular point, they are defined as the product between the mass and the distance. So for a planar lamina with variable density, so now we're no longer looking at a thin rod or at a wire or something that it's one-dimensional. Now we're gonna put it in two dimensions. So we have the following integrals, that is m sub x, that is the double integral of y times the density function dA, and m sub y, that'll be the double integral over the region R of x times rho of xy times dA. Well, what are these subscripts x and y, and why do these double integrals? Here for m sub x we're multiplying by y, and here for m sub y, here we multiply the density function by x. Well, let's have a look at this two-dimensional setting. Well, so this is going to be our center of mass. So if we have this again, if we have this this planar region, this approximate planar region, let me just draw the edge. All right, so notice in this case it has a variable density. It has different shades of brown that describe its density. So the thing here is here this center of mass right there with coordinates x bar, y bar. So here when we look at the x, so when we look at the x point, at the x or the x coordinate of the center of mass, so that's this distance here. Okay, let me use a different color. That's this distance. So x, which is this diagonal line, it's what? It's x. However, notice how this involves a distance y, which is this distance y. So this distance y, that is the distance y, which is the moment about x. All right. Okay. So now, what about the other case? For the y coordinate of the center of mass for a planar lamina, well, in this case, which is going to be, this will involve a distance x, because if this is y, this is another y. Here, this distance will be, this point will involve a distance x. So that's why in this case we multiply by the distance x. That's to find the moment about y. And well, to find the center of mass, again, we divide the total moment by the mass, the total moment by the total mass. Now, here is the thing. Look at this coordinate right here. No, it's not a typo. So this moment about y, which involves a distance x, that goes in the x coordinate, and this moment about x, which involves a y distance, that's why it goes in the y coordinate. So no, it's not a typo. It's not the reverse, right? So let's have a look at one example to see this one in action. All right. And again, I already have the problem written down for you. Let me explain how we set up the problems to make this a shorter video. So here, what are we going to do? Set up the integrals. So there's a few integrals that give the center of mass of the rectangle with vertices at the origin 1, 0, 1, 1, and 0, 1, which is our region plotted to the right, to the left of the screen. And the density function, oh, be careful, because sometimes density functions will not be given by some row of xy equals a polynomial or an exponential or whatever that is. They will be given in a more cryptic way. All right, so the density function is proportional to the square of the distance from the origin. Evaluate the integrals to find the point where a pin should be placed to perfectly balance this region. All right, let's talk about the density function. So the density is proportional to the square of the distance. So that is, density is proportional to the square of the distance. So when we look at proportions, we need to multiply by a constant k. All right. Now, how do we get that distance? Because, so again, if it's from the origin, so that's the point 0 to any point x, y, right? Find the distance between the origin and any point right here. That'll be x minus 0 squared, y minus 0 squared. And that's under the radical that describes the distance. And well, so x minus 0 squared is just x squared, y minus 0 squared is just y squared. And squaring all that, that will cancel the square with the radical. So our density function would look like this. That actually, I'm going to highlight with green so you can see how it looks like. All right. Okay, number one, to find the center of mass, we need to find the center of mass, we need the mass and also the two moments. So that means we will have to evaluate 3 double integrals, one for the total mass and 2 for each of the moments. One for the moment about x and another one for the moment about y. All right. So for the mass, that's a simple one. All we do is the double integral over the square region right here given by these 4 order pairs, by these 4 points. All right. So that means, let's highlight the density function. Okay, and that density function k equals x squared plus y squared, and we're integrating between 0 and 1 and 0 and 1 because here we have essentially the unit square. All right, unit square, that's a square whose length is equal to 1. All right, so let's integrating all this with respect with respect y, then with respect x. I'll just give you the result, which in this case is, what's that? 2/3 k. Okay, and you might wonder, what is that k? Well, that's number one, a constant of proportionality, and number two, that k depends on the material this planar lamina it's made up of. All right. Okay, so number two, let's find the moment about x. Again, be careful. That's because the moment about x involves a distance y. And again, I will replace this density function rho of xy, which will be, again, k times x squared y squared. So here, if we were to distribute the y to these two terms, we will be integrating k times x squared y plus y cubed. All right, and well, I'm gonna skip the integration steps and I will just give you the result, which will be 5/12k. All right. Okay, let's keep going. We're almost done here. So the moment about y, and again, keep in mind that the moment about y involves a horizontal distance, an x distance. Okay. So, integrating rho of x, y, times x, that's integrating k times x squared plus y squared. And this will be, what is that? This will be, okay, like, again, if we distribute the x over these two terms, that would give us, as a result, k times x cubed plus xy squared. All right, and again, I'm going to skip all the integration steps for this, which will give us, as a result, another 5/12k. All right, now that we have the moments about x and the moments about y, let's find the centroid. Centroid, it's another way to say center of mass, by the way, all right, which is the x bar and the y bar. How do we get x bar, y? How do we get x bar? That's the moment about y, which involves a distance x over the total mass, which is, what did we get? 5/12k over 2/3 k. And likewise, for for the y coordinate of the center of mass, divide the moment about x by the mass. That's again 5 over 12 over 2/3. Now 5 over 12 divided by 2/3, that's the same as multiplying by 3/2, all right? Which 3 over 2 reduces to 5 over 4 times 2, which is 5 over 8, right? So the coordinates are 5 over 8, comma 5 over 8. All right, so let's make sense out of this result. So let's move back to the region of integration. So 5 over 8, comma 5 over 8 is going to be our center of mass right here. So I divided this into 1, 2, 3, 4 equal parts. So 5 over 12. So this is no, 5 over 8. So this is 1/2, which is the same as saying 4 over 8. So that means 5 over 8 should be, oh, actually, this is our 5 over 8, 5 over 8. All right. Now, notice in this case, this is where we should place a pin to balance the region. Well, notice it's not exactly in the middle. That's because, well, the density of the material increases as we go away from the origin. So that's why, in this case, well, it makes sense to keep it not exactly in the very middle. All right. Let's have a look at another example. All right, let's move to example number 5. All right, so in this example, so suppose the density at any point on a semicircular lamina is proportional to the density from the center of the circle. So in this case, it's just proportional. All right, it's proportional to the distance. I mean, not to the density, to the distance from the center of the circle, not to the square of the distance like the previous problem. All right, so that's going to give us the following expression. So rho, that density will be k times d. That's proportional to the density, not its square. And again, if we consider this semicircular region, we have this point right here and any point xy in the planar region. So the distance from the origin 0, 0 and any point xy will be given x2 minus x1, that's x minus 0, y2 minus y1, y minus 0. And well, x minus 0 quantity squared, that's x squared. And likewise, y minus 0, which is y quantity squared, that's y squared. And everything underneath the radical. All right, so we're going to follow the same process as before. Number 1, we need to find the mass, which is given by this double integral. So let me highlight the density function. That'll be this rho of x, y. All right. So evaluating this integral k times the square root of x squared plus y squared over a semicircular region. Oh, in this case, to make our integration a lot easier, we're going to use polar coordinates because it's a semicircular region. And no, you don't want to evaluate a double integral in rectangular where the region is circular. That's going to make you create a two-variable trigonometric substitution, which you can do. I mean, you can set it up, but it's not the most practical way to go about. Or I mean, if you want to try it, you want to try that direction, you're free to do, you know. But anyway, we're going to do what's it called, polar coordinates to evaluate this double integral. So here, notice the radius of the circle. Well, it's not given, you know, it's not given. So that's going to be a circle of radius. Let's just say the radius is just a. I mean, could be any number, could be radius 5, could be radius 7, could be radius 9, whatever that is. So iterating this double integral for the semicircle, so we will go for the limit from 0 to a, that is the radius of the circle. All right, that's the radius a. And the angle, oh, what about the angle? Isn't that going to go between 0 and pi radians? Because that's only the upper semicircle, so that explains this 0 to pi for the outer limits of integration. All right, so and changing this function right here, square root of x squared plus y squared, that's the same as saying square root of r squared, which is simply r. So That's going to be our, oh, I already had it here, right? So this becomes right here, this becomes just an r. All right, but in this case, times the r from the change of coordinates to from dA to r dr d theta. So this r right here times this r, that becomes r squared. And integrating with respect r from 0 to a, and then with respect theta from 0 to pi, that's going to give us this crazy expression where k, again, it's just the constant of proportionality given by the density function, and that's related to the material, the planar lamina it's made up of. And a, it's going to be the radius. It's going to be the radius of the semicircular region. So that's the mass. What about the moment about x? And again, keep in mind that the moment about x involves a y distance right here. What is the density function going to be? Again, it's going to be this one right here, all right? This density function, which is, we're given, we have simplified it to k times the square root of x squared plus y squared. All right, but again, iterating this integral from 0 to a, the radius a, from 0 to pi, again in polar coordinates. However, we're going to have an additional factor here, unlike the mass integral. So for this y, recall that in polar coordinates, y equals to r sine theta. All right, so that's why we replace. So that'll give us, that'll reduce to r cubed sine theta dr d theta, and integrating this should give us a to the fourth over 2. All right, again, I'm skipping the integration process. I'm just giving you the result to keep this video short. And in a similar way, the moment about y, which involves, again, be careful, moment about y involves an x distance. And again, let's highlight our density function here, which is, again, this k times the square root of x squared plus y squared. All right. Okay, so again, iterating this double integral in the world of polar, one thing you should keep in mind as well is that this additional factor of x, we need to convert it to polar, that is arc cosine theta. All right. So, and after simplifying the integrand, we should be integrating another r cubed cosine theta dr d theta. And guess what, guys? This integral is going to be equal to 0 without, I mean, I'm skipping all this process, but I mean, how can we tell that this integral is going to be 0? Well, so at one point in this integration process, we should integrate the cosine function. Now, what is the cosine function's integral? Isn't that sine? That's correct. Now, evaluating the sine within the limits 0 and pi, upper limit sine of pi, isn't that equal to 0? Sine of 0, it's also equal to 0. So 0 minus 0, that's 0 times whatever we got from integrating r cubed between 0 and a. So that's what's going to give us a 0. Well, we're going to make physical sense about this. Now let's find the centroid or center of mass. X bar, y bar, where x bar is the moment about y, which involves a distance x, that is moment about y, which is 0, over the mass, that's simply going to give us a 0. And lastly, the moment about the y coordinate, which is the moment about x, which involves a distance y, over the total mass. But well, in this case, the moment about x, which is k a to the fourth over 2 divided by the mass, which is k a cubed over pi. All right, so 0 for the x coordinates, and simplifying powers of a and getting rid of the k's, that's going to give us 3a over 2 pi. Well, let's make sense out of this result. So notice the center of mass, it's 0 for the x coordinate, and it only goes along the y-axis. Well, that's because look at the region. Well, actually, my semicircle is not perfectly symmetric about the y-axis, but I mean, it makes sense to place a pin somewhere here to keep this circular planar lamina imbalance. However, what happens if x and x it's either positive or negative? Well, that's going to go to the sides. That's because in this case it's the density function that tells us that as we increase the radius, it increases the density. All right, so that's the end of example number 5. That's centers of mass in 2 dimensions. All right, in the next topic, we will discuss the mass and center of mass in 3 dimensions. All right. Okay, so to find the center of mass in not 2 dimensions, actually in 3, there's a little typo here in the notes, okay? So again, we're going to have a rho function that is an integrable density function on a closed and bounded region in space. So the mass, the moments, and the centers of mass are computed using the following integrals. So number 1, okay. So here when we talk about the total moments, the total distance moments, okay. So here we need to describe a moment that involves a distance x. So the moment that involves a distance x is going to be the moment about y and z. The moment that involves a distance y will be, let me use a different color here, okay, so it will be the moment about x and z. And lastly, the moment about the moment that involves a distance z will be that moment about x and y. So in this case, we would need to think of this in 3 dimensions. Well, so, and again, look at this this order triple. The order triple that would give us what's it called, the center of mass in space would be the moment about yz, which again involves a distance x. All right, see how it involves a distance x. The moment and divided by the mass, the moment about what's that, xz, which is the one that involves the y distance, right? And lastly, the z coordinate is the moment that involves the distance z, that is the moment about xy. Everything divided by the total mass. How do we get the total mass? Well, we discussed that before a few times in lecture. That's simply the triple integral of a density function of 3 variables, or maybe just 1, maybe just 2, maybe just 3, or maybe the density could be a constant like 5, like 7. Well, it depends. So let's have a look at one brief example. I mean brief because I will just give you the integral setup, but I'm not going to go through the process of evaluating all these integrals, because look at this definition box. Each of them involves a triple integral, another triple integral, so a total of 4 triple integrals. So this is the equivalent of evaluating a total of 12 integrals. All right, so that's going to be a little overwhelming. Okay, so let's have a look at one example. It's already pre-written. Let me explain the details here. So here we will find the mass and the center of mass of the unit cube in the first octant. Okay, so this is key. The unit cube in the first octant, that is the cube that is bounded by the coordinate planes. Hey, again, what are the coordinate planes? Aren't they x equals 0, y equals 0, and z equals 0? Yes, and the planes x1, y1, z1. So that comprises 1, 1, 1, the unit cube. So 1 times 1 times 1, and it also happens to have a volume of 1. All right. Given that the density at the point x, y, z is proportional, again, this is going to take us back to the square of its distance from the origin. So the density here, the density function, rho of x, y, z, is going to be k times the distance squared, where again, if we place these points, so right here is the point is the origin 0, 0, 0, and any point on the cube, that's going to be x, y, z. Let me point this point over there. So what's the distance from the origin in any point? That is x2 minus y minus x1, y2 minus y1, z2 minus z1. All right, that means x minus 0 squared, which is x squared, y minus 0 squared, which is y squared, and z minus 0 squared, that's z squared. Everything under the radical because that's from the distance formula, and then all squared, and see how the radical cancel the square, leaving us with this density function rho of x, y, z. All right. Okay, let's set up the triple integrals that calculate the centers of mass. So number one, let's calculate the mass. Okay, so the mass is calculated by, okay, let me highlight this density function because we're gonna need it. All right. So that's rho of x with the triple integral of rho x y z, which is k times x squared plus y squared plus z squared. And well, the limits of integration, I believe they're pretty straightforward. From 0 to 1, from 0 to 1, and from 0 to 1 for all x, y, and z respectively. Well, again, I'm going to skip the steps of the integration, and well, the result of evaluating this integral will be simply k. All right. Okay, so for now we need to have a look at the moment integral. So the moment again that involves a distance x, that is the moment about y and z. And well, all we do is multiply by x our density function, okay? The limits of integration just remain the same. And well, I'm going to skip the integration, and again we will distribute the x over the three terms inside of the parentheses. I'm also going to skip all this. I think you guys know what I'm talking about. And after integrating all this, the final answer is 7k over 12. In a similar way, we're going to compute the moments about xz, which are xz, which involves a distance y, and the moment about xy, which involves a distance z. And again, we are simply integrating the same, I know it's a lot of work evaluating these triple integrals, but I mean the idea really, the bigger picture, it's simply integrating some functions. So that's going to give us another 7/12 for the moment about x and z, which involves a distance y, and also for the moment about x and y, which involves a distance z, that will also give us 7k over 12. All right. Well, so we have all we need to find the center of mass. How do we get the center of mass? X bar, y bar, z bar. Again, the x coordinate is the moment about yz, which involves a distance x, over its mass, that is 7/12 k over k. And then comma, the y coordinate will be the moment about x and z, which involves a distance y, that's also 7k over 12. And lastly, the z coordinate will be the moment about x and y, which involves a distance z, which is 7k over 12 divided by k. And notice how in this case, all k's get cancelled. Final answer 7/12, 7/12, 7/12. So that means if we divided this in 12s, so halfway through would be 6/12, 6/12, 6/12. That is halfway between. So one more unit, that's 7/12, 7/12, 7/12. So the center of mass for this unit cube, again, will not be exactly in the very middle. That is 1/2, 1/2, 1/2. No, in this case, it will be 7/12, 7/12, 7/12. And this is the end of this video.